Hello, and thank you so much for joining us today, taking the time to watch this session on how to build connected microcontroller apps with FreeRTOS. My name is Richard Elberger, and I'm a technologist in the FreeRTOS IoT team at AWS. What does that mean? Well, I highlight capabilities and inspire the art of the possible, usually at a depth that's useful to our customers actually designing IoT apps and writing code. Now, with regards to this talk, we have a lot of exciting technical approaches here that we have surfaced through IoT team's work in the next generation of IoT protocol libraries and our long-term support release. We commonly call that the LTS release. And we have been talking about that for like the last 6 or 9 months on freertos.org. It's just so cool, and I'm so excited to show you how we made IoT connectivity composable. Let's go ahead and get started. So I'm going to start with this wonderful story from New Zealand. It perfectly demonstrates the complexity that IoT faces when connecting to the cloud from the wild. It surfaces multiple challenging factors, device power, radio range, and throughput. We're not going to run extension cables to cows, right? So these cow-connected devices need to run on battery too. They need to be efficient. When the cow is kilometers away in a pasture, the device won't connect to a centralized Wi-Fi router at that distance, right? So we need to think about low power, wide area networks, radios like LoRa or Cat-M. And when the cow is out in the wild, we likely don't do anything beyond telematics. But when the cow is in the barn, we can do things like firmware over-the-air updates, which would be super inefficient, if not impossible, when you're out in the wild. Beyond that, how are we going to authenticate to the cloud with this device? What do we need to do to keep our connected cows secure, which should be our top priority, right? These are some of the many questions our customers ask, and we will answer them in this talk and many others, right? So since this is a 400-level talk, we need to take some assumptions, right? So we can jump into the details about the physical world of connected devices. Now, first, I would expect you to understand the general definition of the Internet of Things, right? And second, I would expect that you generally understand the basic requirements for connecting to AWS IoT Core's MQTT broker up in the AWS cloud. And third, I would expect that you would have at least some basic understanding of embedded devices like microcontrollers and Wi-Fi modules. And maybe you haven't coded it yet, but at least understand the concepts. And fourth, I would expect you have a working knowledge of writing code, right? Which means you probably have written some RTOS code or multi-threaded code in the past. Now, if you're not working in one of these roles, it's totally okay to continue. But some of the concepts here might be rough going, all right? So just brace yourself. And with that understanding, I'd like to jump right into the next topic about building. You're armed with this knowledge, right? Now what? So let's go through what we're going to talk about in this talk today. First, we're going to talk about hardware. But we're going to talk more about the connectivity choices we're faced with because this influences how we will connect to the cloud. I have a couple of different examples prepared for you. Then next, we're going to talk about how the connectivity libraries have become, how they've evolved. I wouldn't say new because we've had them for some time, right? These IoT connectivity libraries, but they've evolved to be more composable. This is really, really good for implementers, and I'm going to show you why. And then we'll see how this all gets put together at runtime. I'll also talk about IoT device testing at this point. There are some great new tools that you can start using to better understand your device connectivity, reliability, and resiliency. So the first thing I would like to start off with is general compute is not IoT, okay? So IoT devices are usually fit-for-purpose devices. When you buy a connected microwave, the seller doesn't expect you to run Doom or OpenOffice on that fit-for-purpose device. So folks have bantered that a mobile phone is an IoT device, and well, I might have even said that in the very early days of IoT, but that's a general purpose device. And because it's a general purpose device, you need to have good amounts of RAM and storage and other features that drives the prices up. So the functionality of IoT is finite by design, which subsequently brings a lot of positive powers, especially cost. So while, yeah, there are boxes such as general compute industrial gateways, the reality is that the number of those gateways will be much smaller than the billions of sensors in connected devices we're going to see. So while compute and memories continue to be important in your solution design, I would argue that if you're going to get anything right in your IoT design, it's got to be your connectivity module. We continue to see customers struggling with the component choice, and there's a lot of noise in the industry about this or that module being the saving grace for specific use cases. And the reason why this is so hard is that there is so much choice and so many factors to consider. There's distance or range. How far can you go, right? And then there's weight. How much payload can you push across the wire? And this depends on the underlying protocol, right, that you're going to use. And then there's velocity. How fast can you push the bits across? There's availability. How can I move from one geography to another and retain connectivity? There's battery life and security, and again, the important cost factor if you're going to do so many of these devices, right? So security here is about media level security. I'm not talking about storing credentials here. For example, I can't join a cellular network without a SIM, but I can just plug right into an Ethernet network. So that's a lot more accessible with less protection. But looking at this, just don't go by how much green that you see in a particular column. That's not the way to make component decisions. Because it can also create other situational complications, including operational ones. So given that, what you already know is, in order to connect the IoT core, we need to create a secure TLS 1.2 connection, which requires that private key and certificate. Over time, we've narrowed some best practices by working with our customers and partners, especially for the smallest microcontrollers. The choice here is really, really important. TLS is costly from a compute perspective, so you want to be able to offload the crypto operations, all right? Either have the communications module do it, or leverage the secure element or enclave where you can offload the operations. And then, when you're prototyping, you are directly connected the board to your laptop, right? And you're getting direct power, so you may not think about this, but running on battery has other considerations, and having the low power capability isn't always enough. Ensure you're looking at the SDKs that you're getting for your microcontrollers that the silicon vendor provides to help you out with that. For the seasoned IoT folks out there, you know that once you've done a sanity check, that the components work well together, the hardware guys will start designing the PCBA for the development effort, all right? So when I started working on this presentation, I wanted to build a couple of tangible examples, representative examples, really, that we see with our customers. On the left side, you see hardware components that can participate in the IoT that requires a high degree of mobility, right? And then, for example, if I want to continue to have streamlined connectivity from worksite A to worksite B, I will need that long-range, high-mobility connectivity. And on the right hand, you see a configuration that would work within the range of a commissioned Wi-Fi network. So the first example that I have here is a bunch of parts for the high-mobility prototype that I did. There's a lot of different prototyping parts here because they all come from different vendors. The MCU is from STMicro. The GPS is a fantastic breakout board coming from SparkFun, and there's a QuickTel module breakout that's developed by STMicro again. And also we're using a SIM card here that has on it its commissioning information already. What's interesting about Once is that to provision IoT connectivity credentials, you first talk to a server over UDP to get the certificate, and then you talk directly to IoT Core using TCP. So it's really a fantastic solution to get started quickly and for building solutions on top of AWS, and I would encourage you to go take a look at that deeper. Now, when you put them all together, you've probably done this before. The board also has an Arduino header for that, so I was able to wire up the pins to the GPS quite easily. And look at the GPS module, it's already on, right? It's ready. So all you have to do is start reading the UART data. Next, the other board that I used for the limited connectivity mobility prototype, I used this board from Microchip. They've been doing this for years, where they have been building fantastic IoT development kits with their secure element paired with the Wink 1500 family. All right, and those are Wi-Fi modules. If you look closely, the chip just south of that is this, just south of the secure element there is the temperature sensor that I'm reading the data off of, okay? So it's using a PIC24 microcontroller, really low cost, really low power, just a super processor to start using for the IoT, all right? So what are some key points for your solution design here? Okay, what we saw in this section was an overview of component selection. I think that what you can keep in mind here is that there are development boards that align with your use case, right? Don't do it the reverse way. Don't get a development board with a connectivity module that you feel married to, right? Do the analysis about the right module for the right job. And I've seen many times where people felt married to a specific communications module and type and didn't do a deep evaluation of the right module for the job. So now we're going to get into the core of this talk. Now what we have are peripherals in the MCU. What's next? Well, FreeRTOS, all right, supports virtually every microcontroller family out there today. It supports ARM Cortex-M and Cortex-R, which is really the bulk of microcontrollers on the market today. It supports ARM Cortex-A, even though that's not a classic microcontroller. It's an application microprocessor, right? But also, FreeRTOS supports Espressif, it supports PIC, it supports RISC-V. All these architectures can take advantage of FreeRTOS, and FreeRTOS can take advantage of these microprocessors. So let's get rocking, right, on exactly what we're going to do with this. So when you're connecting to the cloud, and that means IoT Core's MQTT broker, as you know, you first need a socket connection from the microcontroller to the cloud using the communications module we talked about in the previous section. We see that represented here in the communications task. That task is responsible for ensuring proper module management, enabling the module and then initializing the module and then commissioning the configuration as you need it. For example, connecting to an access point and getting the IP address and the DHCP. You need to do all of that stuff. We take that for granted on our laptops. Also, you need to take care of all the teardown, like disconnecting from the AP and putting the module to sleep to save power. And this is one state machine that we need to effectively manage here. And so we're not connected to the cloud yet. We're still in the communications task. We need to create that TLS 1.2 socket connection to the cloud. We're walking our way up the OSI stack, right? We need the endpoint, or the DNS address, and we need the server that we're connecting to, right, in order to make the socket connection. And when the socket connection is done and we're connected to the cloud, we're ready to start sending and receiving data. This task also owns the buffers for the communication. So we have proper encapsulation when we're doing this. Now we're ready to move on to the cloud task. effectively, this is the MQTT client. The MQTT task knows a lot about MQTT, but it doesn't know anything about sockets or about the communications module. It doesn't care. It shouldn't care, right? What it does care about is how to handle MQTT from input and output perspectives. So it needs a clean interface about how it can deliver payloads to the communication task. One last word on this slide. You see the XTask notify arrows going across. This is a lightweight mechanism that's used to talk between tasks in a loosely coupled way. Super useful, all right, when connecting the dots between tasks that are sitting in a blocking state, like when we're managing the communication tasks management state, right? So we don't need to continuously keep on running and sucking up clock cycles. We can sit in a blocking state and then other work can happen. So let's build on that. We're going to take a look at how we can communicate to the cloud and take some sensor readings without going crazy with task creation. When doing sensor readings, you usually want to send readings at some predetermined interval. Maybe interval precision is important to you, maybe it's not. But if I have an extra clock on the MCU, on the microcontroller, I'm definitely going to use it, all right? So there's no reason not to. Usually reading the data from a sensor is done over GPIO or an ADC or an I2C bus and, well, more rarely a spline, right? This is just wrapped in a function, easy. Once you get the signal, do an XTask notify from ISR because it's an interrupt to the cloud task that's sitting there in a block state. It's waiting for something to do, right? It gets that signal to go and fetch the sensor reading and then tell the MQTT client to publish it somewhere. The MQTT client wraps that up in a payload and serializes it. And then it pushes the data through that interface exposed by the communications task. This is what we talked about in our last slide. So now we know how we're communicating from the sensor through some required mechanisms and then to the AWS cloud. But there's one more thing I'd like to touch on now, and that is the low power mode. All right, super important. What happens when we go in low power and we're dealing with this communications? Well, let's see. What can we do? We can put the module into a low power or a sleep mode. Okay, and if we do that and the module can't send data, what's going to happen? Well, the socket connection is going to close, right? So when we're in low power mode, nothing is going to be sent to the cloud at all. And going a step further, we can put the MCU into sleep mode as well, right? To save even more power. And microcontrollers have these low power features, usually have a clock or a wake up pin or both, right? That enables us to manage that effectively. So when you're working with low power mode, just realize that this is another area where FreeRTOS can really, really help you. Since if you're working with tasks effectively, which I'm sure you are, you will be able to manage and bring up and tear down these tasks as you go in and out of these states. I just want to put in one more word here about these tasks. Who's writing the code for this stuff? Well, the application task itself would be yours, all right? So would the sensor reading and the low power wake. Only you know what you want to implement for those parts. So would the sensor reading and with the bulk of the code and the communications task, it'll come from the microcontroller BSP, right? Or the SDK for the communication module. And that's going to be all wrapped up into a task as well. Now, the bulk of the cloud task is going to be, well, it's going to come from what is the new and improved, well, the improved MQTT library in the FreeRTOS project called Core MQTT. That will need to be wrapped up in a task, and there's a template code for you to use on freertos.org that you can lift and put into your project. You can call it an MQTT agent, But yes, it's core MQTT wrapped in a task template. That will be super useful for you to get your solution integrated more quickly. So, well, but wait, there's more. There's also an HTTP library that you could work with with the communications task too, if you need HTTP. The core JSON library here is really a utility to help you work with common MQTT payload types. The core PKCS is going to help you work with secure enclaves and secure elements and TPMs and smart cards and other secure stores that have exposed PKCS11 interfaces. This will help you with authentication and crypto operations when making that TLS 1.2 connection. Now, you see those two libraries at the bottom, right? Those are actually hosted by AWS because they deliver on APIs for AWS-specific functionality, which brings up an important point. Although FreeRTOS project is now governed by AWS, it continues to deliver in the kernel and the libraries that do not rely on AWS-specific functionality. All right, that's really cool. So now if you're looking to communicate with IoT Core through regular topics only, then really the only thing you need is core MQTT library. However, there's other things that you can take advantage of when working with AWS IoT Core. One is the device shadow, which is an AWS-specific functionality, so it gets its own library that also needs core MQTT. The other is the jobs library, which helps you manage jobs like over-the-air updates across your whole IoT fleet. That relies on core MQTT as well, which tells us these libraries work with topics. They're special MQTT topics, the shadow library and the jobs library, that start with a $ sigil. But they all need the same thing. The topic publishing and subscribing needs to be configured so that it can start pushing serialized MQTT data to the transport interface. Also, those subscription callbacks are listening to one incoming data buffer, right? That's how we're getting the data into our MQTT task. I think the way that MQTT connections have been simplified here in FreeRTOS has made some really big improvements over the last year. We're looking forward to seeing your feedback on this stuff. So when I was prototyping with the hardware that I showed you, in the last section, I used IDEs from the microcontroller vendors. I just want to touch on this real quick. So the first one here is the ST Micro Q IDE. It's a really nice embedded development environment with a modern FreeRTOS analyzer that you can use to help you develop FreeRTOS apps. So it can help you look at how your app is connecting to the cloud. So you can organize the libraries. Here, what you'll see is that there's a CSDK folder, and that's a little bit of an old school naming convention, and you're not going to see that much in the future. Okay, but it's still using the core MQTT libraries here. The next is the MPLAB X IDE, all right? The way the files are organized in MPLAB X is a little bit different than the STM32 cube that I just showed you. So what I really like about MPLAB X is its plug-in infrastructure. And I use its data visualizer really often. It also has a FreeRTOS task analyzer or visualizer. And usually when I'm working with microchip stuff that's ARM-based, I use Percepio or Seger tools. But with PIC, that's a little hard, so I rely on the tool here. I just hope that they take a look at the functionalities that are in FreeRTOS a little bit deeper here. So room for improvement, I would say. So some key points for organizing code. I wanted to walk through a couple of takeaways here. So as the IoT matures, right, and silicon vendor SDKs mature, we're going to see norming around how we can plug and play code, all right? We want to get in the situation where we can just reuse blocks of code, these composable blocks of code, easily when we're developing these IoT applications, and that's when we can really start accelerating our solutions, all right? So now we're going into the last section here. We're going to take a look at communicating and stitching all this stuff together. It's not just running, it's not just unit testing, but we also need some kind of high-level integration test that's going to validate our resiliency when connecting our microcontrollers that are running FreeRTOS and connecting to the cloud, right? So just a level set from a stack perspective, these are all the tasks that need to work together and how often they run and interoperate with one another. We need to initialize these three tasks on the right, but we also need a task handler for all that stuff. Don't be discouraged by this diagram. We already talked through all of these details, okay? We're just putting them together now. So this is really for your reference on how it all looks together. So if we're running a master application task and all these other tasks are running, how do we have them work together? The details can become complicated, right? But again, we can handle them as a set of state machines. So on the left here, we have an application task that keeps a handle on the other tasks in the mix. We're only fixated on the communications part right now. Of course, there will be the MQTT task, which you'll build in your sensing stuff, or we can call that an agent, right? It's just going to keep on running. But let's focus on the connectivity right now. The two tasks on the right are actually the same tasks, but two different state machines. So that task is started, but we're waiting or blocking on a notification. We're going to walk through this as if connecting to an access point. The app wakes up, right? And either by initialization or coming in from low power mode, the application sends a notification to a task that says, hey, start connecting, and then it goes to work. Then it goes through a series of steps, right, to connect. When done, it signals the application task that we're good to go. To note here, we need to give the communications task the task handle, right? And so it knows how to talk back. Then the application task can move on to the next and talk to the task, the communications task about connecting the socket to the cloud. And when that's done, you can notify the app task again. And this is where you would have the application task doing a block wait and to handle management stuff and that sort of thing from an application management perspective or going back into deep sleep. So, okay, we're just going to spend the next few slides a little bit on testing, right? So we're going to look at integration testing and what we've been doing to help customers build connected apps faster with integration tests. So let's go take a look at that right now. With Device Advisor, it allows you to quickly put together integration tests that are organized into test suites or test groups. If you've used testing software in the past, this pattern shouldn't surprise you too much, right? But what you see here is a bunch of pre-baked tests that you can run for your device. And when you run it, you'll get a high-level result. Here is just a sample of what it looks like. And, well, but the juicy parts are in the details of the run, right? If you look at the qualification program list, this shouldn't be any surprise to you, okay? They're strongly related to the FreeRTOS tasks that we've been talking about through the previous slides, right? So now you can see you have easy access to integration testing for communicating to IoT Core using microcontrollers and FreeRTOS. So that was a bit of a short section for us, but we talked about stitching, which is bringing all of that together. And we skipped over provisioning, right? Why did I do that? Well, in both our cases, the devices came pre-provisioned. That's the new thing, right? We want to have pre-provisioned devices to make our lives simpler. Both the SIM and the secure element, the SIM in the STMicro solution, the secure element in the microchip solution, they were both provisions. So if you're not using these mechanisms, you have a bit more work to do to get your IoT fleet provisioned. To wrap up the section, I can't assert enough how useful an integration strategy can be, and Device Advisor, all right, can help you accelerate that with testing your IoT device connectivity. So let's do a quick recap then. First, remember, don't feel married to a communications module. Do your due diligence for every use case that you have to implement. So it's really easy to fall into some design traps when you're under time pressure. Take the time to properly design and encapsulate your FreeRTOS tasks so you have a much easier time managing your code base. Finally, many optimizations have been made to the application protocol libraries that are now part of your FreeRTOS project, including memory utilization enhancements. All right. Your next step would be to take a look or a deep look at freertos.org. The content has been refreshed and is really, really increasing. It's really cool and fun. Also, take a look at integrating Device Advisor into your integration test pipeline. This will surely reduce the amount of test code you'll need to write yourself. All right. And then much of the hardware I've shown today is available in the Partner Device Catalog. Go take a look. And of course, go build stuff and have fun doing it. That's the best part, right? That's the coolest part. So before we end this talk, I want to give you a note on a customer we worked with in the FreeRTOS LTS release that I've been talking about. Woodside is a fantastic IoT customer in Australia. They needed LTS because they felt they needed a higher level of insurance on the longevity of the code they wanted to use. So I'm really looking forward to see what will happen next or what we'll do next with Woodside after this, right? It's really cool stuff. So thanks. Thank you so much for taking your time today watching this session. And feel free to contact me through any of these channels that I have here. Sample code is available on both the FreeRTOS organization and my own repos on GitHub. So I encourage you to go check it out. And also, finally, please don't forget to take the survey. I do look at feedback so we can continuously improve content. And with that, thank you so much. And enjoy the rest of the conference.